hopefully most of you were able to realize that there is only one way your teacher can fill those seats that are left, right? There's Pam, Ryan, and Sophie left, and there's only 3 seats, so they're all going back to the table. Since their order does not matter, it is different than the permutation we did yesterday. When order does not matter, it is not a permutation, it is a combination. It's how many different combinations of students can she put on the back table. There's only one combination left, Pam, Ryan, and Sophie. It doesn't matter where they sit. So that is my answer. This changes the problem from yesterday because it limits your amount of options. Yesterday our answer was 6 ways. And today it's 1. Now, combinations can be solved in a very similar manner to permutations in terms of lists and tree diagrams, but you have to be careful to understand whether or not order matters or does not matter. So let's do a couple examples together. Our first one. Mrs. Johnston has 5 books she wants to put on the summer reading list. We'll just call them Book 1, Book 2, Book 3, Book 4, and Book 5. Okay? 5 books she wants to put on the summer reading list. There's only 2 spots left. The principal says you can only have so many books on the reading list, and she only has 2 remaining. Alright, only 2 left. How many different combinations of books can Mrs. Johnston put on the reading list? Now, order obviously doesn't matter. If a book's on the reading list, it's on the reading list. So, in order to solve this combination problem, we're going to make a list of the possible combinations of books that Mrs. Johnston can put onto the reading list. So let's start with the first book, book number 1. Okay? Book number 1 can be paired with 2, 3, 4, or 5. Okay? Now, let's start with book number 2. Number 2 could also be paired with number 1. However, we already listed that. These are the same since order does not matter. So we don't want to repeat ourselves. So we'll list book number 2 with 3, and book number 2 with book number 4, and book number 2 with book number 5. Okay, so we've done 1, we've done 2. This is the easiest way to make your list, is to stick with a similar first number. Moving on to book number 3. 3 and 1, well, that's already happened. That's right here. 3 and 2, that's already happened right here. So neither of those are worthwhile. By 2. There we go. So we move the 3 down to 4, with 3 and 4, and 3 and 5, because those are new combinations. And now let's move on to book 4. Book 4 has already been matched with 1, 2, and 3, so the only thing left for book 4 is book 5. Book 5 has already been matched with 1, 2, and 3, along with 4, so there's nothing left for him. This is my sample space, or my total number of combinations that Mrs. Johnston can put. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the answer to this question is 10 different combinations of books that Mrs. Johnston can put on the reading list. Alright? There's not as quick of a shortcut as we learned for the permutations with the counting principle, but you just can easily think through the problem, set up a list, or a tree diagram, which we're going to do with our next example. Alright, so you're at Jimmy John's, and your best friend says you can only order the number 1, the number 2, number 3, or the number 4. You only have 4 sandwiches to choose from. Alright? These are your sandwiches. You have to choose from those 4. After you've picked your sandwich, you have to choose your drink. we'll say there's Coke, water, iced tea, and that'll be it. So those are your 3 options for drinks. You still feel a little bit overwhelmed because you tell your friend, I still have so many choices to make, and he says, no, you really don't. There's 4 sandwiches, 3 drinks, you only have 7 choices, it's not that bad. How would you prove your friend wrong? The easiest way to answer this problem, to show him how much smarter you are, is to draw a tree diagram. You have one set of options followed by another. So if I started off with sandwich number 1, I could then choose between a Coke, a water, and a tea. If I chose sandwich number 2, I could choose between a Coke, a water, and a tea. If I chose sandwich number 3, Coke, water, tea. Hopefully you're seeing the pattern. 4, Coke, water, tea. So how many different choices do you actually have? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You do not have 7 choices. You have 12 choices. Now hopefully you still remember how to use tree diagrams like this from the beginning of the unit. If not, they're pretty straightforward. You break down your choices and go from there using the information from the problem. We had sandwiches first, followed by drinks, so I could get the number 1 with the Coke. I could get the number 2 with a Coke, number 3 with a Coke, number 4 with a Coke. It's very similar to the lists that we just made for the last problem, but it's a little bit easier to organize, especially as you get to more complex and complicated problems. So these are what we call combinations. The order does not matter, but we can still figure out the number of choices. It's just going to be a smaller sample space than when we did the permutations yesterday. Good luck with the problems, and I'm sure you'll do well.